Okay, so the point of this video is to derive how we can describe non-uniform circular motion and the acceleration that happens in non-uniform circular motion, which means speed is not constant. So the magnitude of the velocity is changing. And a reminder that the reason I'm doing this as a video instead of doing this derivation on the board in class is this will allow you to pause it and work through it on your own as you go, right? So if you're not sure how a step works, pause the video, see if you can think through and figure it out before you watch the rest of the video, okay? So in class, we talked about, we had a coordinate system that looks like this. We had something that was undergoing uniform circular motion, like I'm drawing here, where our magnitude of our velocity was constant as we went around the circle, okay? Then we said we could write down that the centripetal acceleration was negative v squared over r, x over r I hat plus y over r j hat, where this has a constant magnitude and this part here is a unit vector pointed radially from the origin. And then due to this negative sign, that means our centripetal acceleration is pointed toward the center of the circle at all times, okay? Now, the derivation that we did in class relied on the idea that r delta theta, let's draw our theta here, delta theta is here, so our arc length traveled over some time interval, delta theta, over some time interval, delta t was r delta theta, and that gave us a distance vt. So this is only true if v is constant, okay? What's always true is that arc length covered, traveled by the object, can be given by the integral of the velocity over some time interval, okay? And so if v is a constant, then we recapitulate this formula here. But if v is not a constant, then this is not true, but r delta theta is still equal to the integral of v, okay? And then we can always write that x is r cos delta theta and y is r sine delta theta. These just come from the geometry that we drew up here, right? And so now we can substitute in this expression for r delta theta into these equations, okay? So that next step of this derivation is going to be the same as what we did in class, the same approach of substituting in for delta theta. It's just that now we have to use this integral of velocity instead of the constant, okay? And so I'm just going to show this for x. It's very similar derivation for y, and I'll let you work that one out on your own, okay? So r cos theta of 1 over r, integral from 0 to t, v of t prime dt prime. Remember, these primes here are not a derivative. These are their special, like, we're using a second t variable, so we're giving it a prime, okay? All right, so we've got this expression for x, and now we want to take a derivative of it to find the velocity in the x direction, and then we'll take another time derivative to find the acceleration in the x direction. I'm going to remind you again, and I'll talk more about this at the end, but what we said in class is the reason this math is kind of complicated is because this coordinate system that we're using, our Cartesian coordinates, are not very good for describing this in a simple way, okay? The reason that the centripetal acceleration formula up here even looks fairly complex is because our unit vector pointed toward the origin keeps changing direction, okay? If we picked a coordinate system where we said just point something toward the origin instead of needing to describe in terms of x or y. This would be much simpler, okay? And we'll find the same thing for non-uniform circular motion. Okay, so now let's take our next step of differentiating this equation with respect to time, okay? So that's going to give us dx dt, which is our vx. And that is going to give us negative v of t sine 1 over r integral 0 t v of t prime t prime. This is basically used the chain rule to do this, and the 1 over r inside our cosine canceled out with the 1 over r outside. Okay, if you want to take a moment and work that out on your own, why that's the case, then please do so. Okay. All right, so now this gives us v of x, and now we want to do the same thing again to find a of x. We'll take another time derivative. Okay, and now we can say that we get v squared over t, over r, cosine of 1 over r, 0 to t, t prime, dt prime. This coordinate is pretty much the same as that one. This derivative is pretty much the same as the one we did in class, but now we also need to consider the derivative of velocity with respect to time, since that is no longer a constant, okay? So we take that and multiply it by r sine. Okay, all right. Now, this thing looks very ugly, but we can actually quite simplify it if we notice that this part, right, looks very much like our definition of x up here, right? And I didn't write out y, but y looks like this one here, right? So we can write this as negative v squared over r times x over r minus dv dt times y over r, okay? And I'm not going to show all the steps for a y, but similarly for a y, you will find negative v squared t over r times y over r plus dv dt x over r, okay? So this thing was looking pretty ugly, but let's see if we can find a way to simplify it, to play with it a little bit and simplify what it looks like, okay? So we're going to start by writing this ugly thing in vector form, right? So our total A is negative v squared over r times x over r minus dv dt y over r times I hat. That's my ax component. And over r y over r plus dv dt x over r times j hat, okay? That doesn't look better yet, but let's keep going, and let's put all the terms that have a v squared over r in them together and all the terms that have a dv dt in them together, and see if that helps us clean this up at all, okay? So that will give us negative v over r, v squared over r, x over r I hat plus y over r j hat plus dv dt negative y over r I hat plus x over r j hat. Okay, this first part on the left here should look familiar. That was the acceleration, the centripetal acceleration that we found earlier. So that's AC. It's always pointed back toward the center of the circle because this vector x over r I hat plus y over r j hat is a unit vector that's pointed toward the center, toward the outside of the circle. And then there's a negative sign, so the centripetal acceleration is pointed toward the inside of the circle. Now, what about this other term over here? Can we do anything? Can we notice anything about this? Well, negative y over r I hat plus x over r j hat. This is another unit vector, right? It's got the same, it's got a magnitude of 1, just like the first one did, okay? And this one is a unit vector that points, let's think about our point here. So we've got our point here, and it's pointing in the negative I hat direction and the positive j hat direction, something like this. If you find the magnitude of that vector, you will find that this is a vector that points tangential to the circle, okay, in the same direction as the velocity. So we call this thing the tangential acceleration, okay? So now we can write our acceleration in terms of a centripetal acceleration that's directed toward the center. That's the part that's causing it to change direction. And a tangential acceleration that's directed along the tangent to our circle. That's about the part that's causing it to change speed. Okay? And the magnitude of that AC is v squared over r. And the magnitude of that AT is dv dt. Okay? Now, finally, lastly, I want to give you a qualitative understanding of where this comes from and how we might be able to do this in a simpler coordinate system. Okay, so if we go back to our picture of our object going around the circle, and we said, let's just say that it's velocity, we could write as some function velocity of t in a direction I'm going to call theta hat, okay, which always points tangential to the circle, okay? Now, if I imagine taking the time derivative of this velocity, I'm going to take the time derivative, oh, sorry. Sorry, iPad problems. Take the time derivative of this thing on, I don't know, that text box is determined to be there. We're just going to ignore it. Of v of t times theta hat, okay? So we need to think about the derivatives in this case of both the velocity and of theta hat, right? We're used to the unit vectors having a derivative of 0, but in this case they don't because they're constantly changing directions, right? So we can write this as dv dt times theta hat plus v of t times d theta hat dt, okay? Now, I'm not going to make you worry about how you would find this d theta hat dt, but I will just tell you that it will be it will have a magnitude of negative v over r and be you could write it like this, negative v over r times r hat. Don't worry about how we derived that, but just imagine that let's sort of explain this qualitatively, right? So theta hat is constantly changing directions, and it's changing directions in the same way that the velocity is changing directions by moving a little bit more toward the center of the circle each moment in time as our object goes around the circle, okay? And so having it have a direction toward the center of the circle should make sense. And we should say it's changing faster with a higher velocity, right? And it also needs to change faster if our circle is smaller, because that would mean it needs to go all the way around the circle more quickly. So qualitatively, this should hopefully make sense, okay? And then this other term, so this is our AC, okay? And then this other term here is the one that's changing in the direction of that tangent vector, and it's changing however velocity changes. And so that is our tangential acceleration. So if you used a coordinate system like this math would be much simpler, but you'd have to deal with this complication of your unit vectors constantly changing direction. Okay? And that's the end of this video for today.